Okay, so we're continuing on here in the gas chapter. Um, we've obviously started talking about gases, and as you saw last time, and as we've talked about before, there's a number of sort of gas laws obviously involved here, and we've talked about a lot actually last time. We got through a good number of them. So let me just kind of talk a little bit about what we talked about last time. Let me get everything. There you go. So with gases, obviously pressure is a big issue, and when we talk about pressure, we usually have kind of three common units that are used, and that's ATMs, that's millimeters of mercury, and that's torr. Um, so in that situation, we can kind of go from one unit to the next. And the way that we do that is to use really 760 as our kind of conversion factor to go from one unit to the next. Remember that a millimeter of mercury is the same thing as a torr. And again, if we have atmospheres and want either a millimeter of mercury or a torr, we multiply. I guess I should have left room there, huh? Multiply by 760, and that will get us millimeters of mercury. Obviously, if we have one of those 2 millimeters of mercury, our torr, really, we divide by 760, and that will get us atmospheres. Now, we started talking about really sort of gas laws as well last time. And remember, there's really sort of three sort of variables that we deal with a lot in gases, and that is pressure, volume, and temperature are sort of our three sort of variables that we all the time come across. We started out talking about sort of Boyle's law. And Boyle's law really dealt with the pressure and volume relationship holding constant temperature. And that's P1 V1 equals P2 V2. And here again, the pressures can be any unit you want as long as they're the same on both sides. The volumes should be any unit you want as long as they're the same on both sides. And in that particular case, there was a certain relationship that we talked about, and that was basically as the pressure went up, the volume went down, and vice versa. Obviously, as the pressure went down, volume went up. So sort of a inverse relationship of each other. One goes up, the other goes down. We also talked about Charles' law. Charles' law really dealt with volume and temperature, holding constant pressure here. And that gave us a V1 over T1 is equal to V2 over T2. Here again at constant pressure. Volume can be any unit you want. Temperature, though, much like all gas laws, do has to be in Kelvin. So pretty much every temperature that you got going on there does need to be in Kelvin. As we saw with that graph the other day, basically if you kind of bring everything back, no matter what gas it is, do sort of a volume temperature sort of graph, you will always end up at the same point, which is minus 273.15, which is considered absolute zero. And that's why, again, we typically need to convert things into Kelvin. The relationship here is pretty much as one goes up, so does the other. So as the temperature goes up, the volume will go up as well or increase. Again, that's really how it's able to maintain that constant pressure. The volume pretty much adjusts for the temperature change, and vice versa. If the volume goes down, then the temperature goes down. We also saw one that's similar to this, was this guy Lucic's law, and that dealt with pressure and temperature holding volume constant. And it is P1 over T1 is equal to P2 over T2. Same deal as before. Pressure really can be any unit you want as long as they're the same on both sides. Temperature here again needs to be in Kelvin on both sides. And the relationship that we saw here was as the pressure went up, so did the temperature. And as the pressure went down, so did the temperature. And that is really because we are locked in here at constant volume. So at constant volume, basically it's not going to be able to adjust. So it's going to be locked into place. So as you increase the temperature, for example, gas molecules will fly faster. Faster they fly, more collisions, more pressure, and vice versa. As you drop the temperature, everybody's going to fly around a little slower flying, less collisions, and thus we will see the pressure go down. So because the volume is really not adjusting like it is here to keep that constant pressure, that's again why we do see the pressure change here when we look at this relationship. We also saw our good friend Avogadro. He also had a law. Avogadro's law is V1 over N1 is equal to V2 over N2. This is actually at two sort of conditions. This is at constant pressure and temperature. Volume here can be any sort of relationship. Our units, again, as long as they are the same. N is the moles. And we also saw this relationship in terms of sort of stoichiometry. So basically, as the volume sort of increased, they're really proportional to the number of moles. So in a sort of gas stoichiometry problem where you're at constant pressure and temperature, you can do a kind of liter to liter relationship, very much like you would do a mole to mole relationship in a traditional stoichiometry problem. So that's sort of an aspect there of Avogadro's number. Now, sort of putting all these sort of gas laws together, I think we finished up talking about the ideal gas law. And that is PV is equal to nRT. PV is equal to nRT basically is different than the previous gas laws, is different in the sense that all the other ones really have twos of everything, two pressures, two volumes, maybe two temperatures. This is sort of just a one sort of situation that's occurring. And we don't have sort of like a before and after type of thing. It is also the most restrictive in terms of units. So in terms of units, P is pressure, which has to be in atmospheres when you use the ideal gas law. V is volume, which has to be in liters when you use the ideal gas law. N, which is moles, should obviously be in moles. And T should be in Kelvin as it's the temperature. And really the reason for all that is the value of R. R is 0.08206 liters times atmosphere, Kelvin times mole. So the gas constant here basically has those units, and it really is sort of what determines, the units that you need for everybody else to be sort of correct. Also good if you ever forget, you could just look at the units associated with R and you'll know what everybody else needs to be in. Again, we talked about sometimes people will use this sort of rounded version of the number, which is perfectly fine if you want to do that. Let's take a peek back here. Yep. Any questions on that so far? I think that's sort of where we left off. And clearly you do need to know these sort of formulas here. All right. So we'll continue on here talking about then the ideal gas law and sort of see what we got going on. So another sort of relationship that's an important relationship, and especially dealing with sort of the ideal gas law as well, is one that was referred to as STP. And STP does stand for standard temperature and pressure. So standard temperature and pressure is STP. And when somebody says STP in a problem, for example, they are actually giving you two values. And the value it means is that the temperature is 273 Kelvin and the pressure is 1 atmosphere. So when it is stated in a problem that this is occurring at STP, then automatically you could kind of insert, if you want, that temperature value and that pressure value into something like the ideal gas law, And that's sort of where we would be in terms of pressure and temperature. Now, there's actually a sort of a special relationship, I guess is the way to put it, that occurs at STP conditions only. And at STP conditions, there's basically the second sentence there that 1 mole of any gas will have a volume of 22.414 liters. Again, really important here is that this is at STP only. So if you are not at 273 in 1 atmosphere in terms of your pressure and temperature, you cannot use that conversion factor. Why would you want to use a conversion factor? You might want to use the conversion factor because it might allow you not to have to do the ideal gas law. So you could maybe sort of sidestep using the ideal gas law to solve a problem. If you're at STP conditions, you could use that conversion factor. But again, it does have to be those STP conditions. If you're not at STP conditions, you probably need to solve your problem using the ideal gas law. But if you are at STP conditions, again, you can kind of use that relationship. Do you have to use that relationship if you are at STP conditions? The answer is no. You could absolutely just put the temperature as 273 into the ideal gas law, pressure is 1 atmosphere into the ideal gas law. You'll get the same answer. So ideal gas law you could use really for any conditions, STP, regular conditions, whatever conditions you want. But if you want to use that conversion factor, it 100% has to be STP conditions. This is also how we get the value of the gas constant if we really put into here STP conditions and solve for R, rearranging our gas law by really dividing N to T to the other side. We get that value for the gas constant as we see there on the bottom, which is basically 0.082057. And again, rounded to either 0.08206 or 0.0821. Any questions on that there? Yeah. So why don't you give this one a go? We want to calculate the pressure exerted by 1.82 moles of SF6 gas in a steel vessel, volume of 5.43 and a 69.5 degrees Celsius. Take a couple minutes, see what you come up with. Let's take a look. So as we talked about last time, sometimes it's a really good idea just to pull out the information from the problem and kind of see where it leads you in terms of these gas laws. So obviously we're looking for a pressure here. We have moles, which is 1.82. We have 5.43, which is definitely a volume. And we have a temperature, which is 69.5 degrees Celsius. So just by looking at that, you could kind of see the ideal gas law obviously would be the correct choice here. Plus, we don't have like 2 pressures, 2 volumes, you know, any of those type of things. So if we think about a couple of things, we're looking there for the pressure. We do have the volume, the moles, and the temperature given to us. We always have R, even though it's not given to us. Again, it's a constant. So again, you always have that value. So we're good to go. We just got to do maybe a conversion here. Moles are okay in terms of units. Liters are okay in terms of the units. Celsius is not okay, so we do need to add a 273 there, and that's going to get us 69.5 plus 273. Looks like a 342.5 Kelvin. And now if we take our PV equals nRT, here we're going to solve for P, so we're going to bring V to the other side. So P would equal nRT divided by V. Putting in our numbers in the right spot there gives us 1.82 moles. Our gas constant there of 0.08206. And our temperature 342.5 Kelvin. All divided by our volume there, which is 5.43 liters. In terms of units, moles will cancel. Kelvin will cancel, and liters will cancel, going to leave us atmospheres, which is good since that is what we're looking for here. So we got 1 0.82 times 0.08206 times 342.5, all divided by 543. Looks like it's a 9 point, try that again, 1.82 times 0.08206. I hit a wrong number there, 342.5 divided by 5.43. There you go. We got 9.42 atmospheres, which is good because we're looking for a pressure. Any questions on that particular one there? Okay, so why don't you try another one here and see what we got. What is the volume in liters occupied by 49.8 grams of HCl at STP? A couple of numbers that might be helpful. Hydrogen 1.008 from the periodic table and Cl 35.45 grams per mole. All right, take a minute or two to see what you come up with. We're looking for the volume, and we have 49.8 grams of HCl. And we have STP. So remember that STP means that the temperature is 273 Kelvin and the pressure is 1 atmosphere. So we got pressure, temperature, we're looking for volume. We don't have moles, but we do have grams, which we can easily obviously get moles from pretty quickly. So that again should really point you in the direction of PV equals nRT. Here again, we're looking for volume, pressure we got, temperature we got, R is a constant. We just need to do that conversion there first to get our grams into moles. So we want the molar mass of HCl, which is basically just adding that. So 1.008 plus 3545 gets us 3646. So the first thing we would want to do is take our 49.8 grams of HCl. We then would want to convert it into moles using our molar mass of 3646 grams per mole. That's going to give us 49.8 divided by 3646, 1.3, we'll call it 7, why not? 1.37 moles of HCl. We now have the moles part. We could obviously use our ideal gas law here and solve for volume. So we'll bring pressure to the other side. Volume would be nRT divided by P. Putting in our numbers, 1.37 moles. Our gas constant, our temperature, which again is 273 from our STP, and all divided by our pressure, which is 1 atmosphere, again, also from the STP. Moles cancel, Kelvin cancel, atmospheres cancel, going to leave us the units of liters that are left, which is good since we are looking for a volume, and it looks like maybe 30.6 if you don't round to 1.3, 30.7 if you do round to 1.3. We'll go with that. We'll use the rounded number. I think that gets you the other one. Question on that calculation there. Now, could you have solved this a different way? And the answer is, yeah, you could have, because this is STP conditions. So you could have used at STP conditions what we just saw, which was 1 mole of any gas is equal to 22.414 liters, which means you could have, if you wanted to, in this particular case, again, because it's at STP, pretty much just picked up from right there where our moles are and basically took our moles of 1.37, using this as really a conversion factor, 22.414 liters up on top, 1 mole on the bottom. They cancel. That ends up getting us 1.37 times 22.414, 30.7 liters, exact same number as you got upstairs there. So again, it gives you a variety of a couple of different ways you could solve it, but again, only could solve it because of it being STP. and you could use that conversion on the bottom. Again, if this was not STP conditions, you could not do it the bottom way. You would definitely have to do it the top way. But again, demonstrates that if you can't remember that conversion factor or not sure you should use it, you could always use the ideal gas law. So you could always just go into it. Any questions on those? Okay. So then let's talk about, another gas law, because, we got some room maybe for it on the page. So we've talked about up to this point, sort of using the three variables, maybe two of them at a time. But here we're going to actually be using all three variables at once. So what happens if we sort of change one of those three variables and we're looking at all three of them? Well, we could really get to this gas law on the bottom by taking sort of the ideal gas law and solving for R and ideal gas law and solving for R. Since this is a constant value, that 0.08206 number, we could set both of these guys equal to each other. And most of the time when you're dealing with gases, as long as you don't open the lid, the number of moles that are flying around in there are probably going to remain pretty constant as well. This reduces us down to what is sometimes referred to as the combined gas law. And the combined gas law is P1V1 over T1 is equal to P2V2 over T2. The pressures here, again, not important which unit you're in, as long as they are the same. Volume, same deal, as long as they're the same. Temperature, pretty much like every single gas law, again, has to be in Kelvin in that particular point. This is the one probably that gives people the most difficult time in terms of rearranging. So just remember that, as we talked about, if you kind of go across the equal sign, you just do kind of like a cross multiplying type thing. So if it was on the top, it should end up at the bottom. If it was on the bottom, you need to move it to the other side. It should end up on top. So it kind of crosses over, to the opposite location when you're redoing it. So this is a nice gas law. It obviously deals with all three variables at once. The other nice thing about this gas law is you could really use it to pretty much get all the other gas laws that we talked about. And what I mean by that is if you think about, for example, if you think about Boyle's law, which means constant temperature, so you essentially just take out your temperature part, and there's Boyle's law right there. You then can think about Charles' law, which is at constant pressure. So you take those two guys out. There's Charles' law right there. You then can think about Lucic's law. I don't erase the entire thing here. Do a little construction back and Lucic's law, which is at constant volume, is at that case. So constant volume means, again, you just kind of take out the volumes, and there it is right there. So kind of a helpful one. You could kind of memorize this guy here, and then you pretty much just take out whatever is being held constant, and you'll have kind of the right gas law back to you, once you don't erase the entire thing like I just did there. All right, so that's a nice little thing about this one. Again, you could kind of get to really the gas law that you're maybe looking for. All right, so let's try this and see how we do on the rearranging front. Consider a sample of oxygen gas, 27 degrees at 9.55 and a pressure of 297. We change the pressure to 8.25 and we heat it to 125. Calculate the new volume of the gas. So take a minute or two to see what you come up with. Okay, so let's take a look here and see how we're doing. So again, if you're not sure sort of where to start or what gas law to use, even though you probably have a good idea in this case, we pull out the information. We have obviously a temperature that's 27 degrees Celsius. We have a volume that is 9.55 liters. We also have a pressure there that is 2.97 atmospheres. We changed the pressure to 8.25 atmospheres. Pressure goes up. Volume is what we're looking for, and we have another temperature that is 125 degrees Celsius. So just by looking at it, you can kind of see it is that combined gas law that looks pretty good and sort of matches here. So again, we would do our P1 V1 over T1 is equal to P2 V2 over T2. In terms of pressures, we're okay. They're both the same unit. In terms of obviously temperatures, not so okay. So we need to do a little 273 adding there. That's going to get us, looks like 300 Kelvin. And adding to our other side here, looks like 398 on that one. Okay. Now we're all in the right sort of units. We are going to be solving for V2. So again, basically you would multiply T2 to the other side. You would then divide by P2. Or again, if you just kind of want to cheat in that case, I guess, and not really think about the math part. This guy's on the bottom. He needs to move to the other side. He's going to end up on top. This guy's on top. He needs to move to the other side. He's going to end up on the bottom. And if you do that, you will end up with V2 is equal to, we have basically P1, V1, T2, bringing that up to the top. And on the bottom there, T1 and P2, bringing the P2 to the bottom. So again, basically as they go across the equal sign, ends up in the opposite location. That's really important because we want to make sure, obviously, we put the numbers in the right location. That means up on top should go our 2.97, which is our P1, our V1 being 9.55 liters. And now our T2 that we moved across should go up there on top, which is 398, all divided by bottom there, which is 300 Kelvin, which is our T1, and our P2, which is our 8.25 atmospheres. Any questions up to there? At this point, we got some atmospheres that are going to cancel. We got a Kelvin that's going to cancel. And that does leave us liters, which is good since we are looking for a volume. And in this particular case, if we do that, looks like 2.97 times 9.55 times 398 divided by 300 and divided by 8.25. Looking like we're going to end up with a volume of 4.56 liters in this particular case. Any questions on that calculation? Now, does it sort of fit with the information that we're seeing? Well, we do see that our temperature increased, and our temperature increased, which we see our pressure increased. And really, probably the only way for that to happen is our volume went down, right? So volume went down, temperature went up, means gas molecules, a lot more collisions in that smaller space, relying on that larger pressure and that smaller volume. So it does sort of make sense based on just logically sort of thinking about what's happening. Any questions on that there? So rearranging these equations, really important. And like I said before, it is a very common mistake, or really two very common mistakes, especially with this one. One is really the rearranging, not rearranging it correctly. Second is maybe rearranging it correctly, but putting like, for example, P2 up on top and P1 on the bottom when you actually put the numbers in. So you want to be doubly careful as you do these to make sure that you not only rearrange it correctly, but do end up actually putting the correct sort of numbers in the right location. Any questions on that? All right, so let's talk a little bit about some gas laws or things that you calculate for gases that you might not have talked about before. And this is, we could actually look at or figure out the density of a gas and also the molar mass for a gas. So first off, when we talk about density of gas, density is mass over volume. And we do get this little part of our gas law here. This is our pressure, which is in atmospheres. That M is our molar mass. which is in grams per mole. R is our gas constant, which is our 0.08206. And that is our liters atmosphere Kelvin mole. And obviously, this guy here is our temperature in Kelvin. So what do we end up with in terms of units, and what happens when we sort of figure out the density of a gas? Well, as we talked about earlier, a reminder that the units that we sort of associate with the density of a gas is oftentimes different than what we associate with the units of a solid or a liquid. So if we just slap into that formula there our units, we have atmospheres, we have grams per mole, we got on the bottom our liters, atmosphere, Kelvin mole from the gas constant, and we have our Kelvin. So Kelvin will cancel, moles will cancel, atmospheres will cancel. The two units we are left with are the typical units of density for a gas, which are grams per liter. So if you remember again, the units that we typically associate with density for a solid or a liquid is actually grams per milliliter, right? So this is slightly different than what we have there. You could also find the molar mass of a gas by taking the density, which obviously here is grams per liter, our R, which is our gas constant, our temperature, which is in Kelvin, and our pressure, which is in atmospheres. And what do we end up with molar mass? Well, we end up with what we might expect if we put in our units for this guy. That is grams per liter. Again, we have our liters, atmosphere, Kelvin, mole for R. We have our Kelvin, and all divided by our atmospheres. Atmospheres cancel, Kelvin cancel, and liters cancel. Leaves us with the typical units of molar mass, which are grams per mole. So these are two formulas that you can use to sort of calculate these things. They're really based off of the ideal gas law, both of them. So they're actually based off of the ideal gas law, P equals nRT. For example, if we solve for N over V here in the ideal gas law, N divided by V is equal to P over RT. You might be wondering, well, what does that equal? Well, N in the ideal gas law is moles. V is liters. That is basically the molarity, right, of our gas by solving for N over V. When you do that, that is the moles per liter. You then can times it by the molar mass from the periodic table. The moles will cancel, and you end up with grams per liter. That's exactly where this formula comes from. So if you ever can't remember this formula, you could always use the ideal gas law to do that and figure it out. And just to kind of show you where it all came from, if you look at what I just did there, that's probably not the best color there to highlight with. Let's go with this one. Obviously, rearranging that ideal gas law for N over V is this part of the formula right there. And obviously, this last part where we multiply by the molar mass right here is that part right there. So again, it's really a derivative of the ideal gas law, and it's a good thing to remember that, again, if you can't remember the specific formula, you could absolutely kind of get yourself there by solving for the ideal gas law. This one too really does come from the ideal gas law as well. If you take PV equals nRT, typically in these type of problems, they give you the grams. So right off the bat in the problem, they give you this problem down here, which means you actually could just solve for N in the ideal gas law, which would be PV over RT. And basically you could just take then the grams divided by N, and that will get you your molar mass basically. So for example, obviously if you flip this around and put it on the bottom, you will end up with P and RT up on top. and everything else will sort of cancel out in that particular case. So, you can very easily sort of use the ideal gas law to get to both of these sort of formulas, just in case, you can't remember one of these guys. Any questions on those formulas there? So why don't you try one? Why don't you try, why don't you calculate the density in grams per liter of nitrogen gas at 27 degrees Celsius and 1.25 atmospheres. And that's about it. Yes, so that's all you should need. There you go. Nitrogen is 14.01 grams per mole. All right, so take a couple minutes and see what you come up with. That is at 27 degrees Celsius and a pressure of 1.25 atmospheres. All right, so again, nitrogen 1401 grams per mole. So again, if you can't remember the sort of formula that we just saw on that slide, wish you were looking at that slide, so I would imagine you can remember it. But just in case you can in the future, I'm going to show you again how to use the ideal gas law to really get you to where you need to go. So again, PV equals nRT. Looking for density here, we really can start with trying to get to moles per liter, which is the molarity. Again, that basically means that we're going to take the ideal gas law and solve for N divided by V. To do that, we divide the V to this side, we take RT and divide it back to that side. And when we do that, we end up with P over RT. This is good because if we look at the information given to us, we have a temperature, we also have a pressure, and obviously R is the gas constant. So you can see with just those two pieces of information, doing a little bit of rearranging here is going to allow us to get too close to what we need. So that's where we'll start. We obviously need to convert our temperature into Kelvin. So that looks like a late here. I'm gonna grab my calculator. 27 plus 273. That looks like a 300. That's good. All right, so solving for N over V will get us our pressure, which is 1.25 atmospheres, our R, which again is a constant. You always have that number available to you. And then our temperature, which is 300 Kelvin. And again, here we can see by looking at the units, atmospheres will cancel, Kelvin will cancel. We basically have liters over moles, but when we divide, right, it flips the other way and becomes moles per liter. So we do end up in sort of the units we're looking for. 1.25 divided by 0.08206 divided by 300. Going to get us something in the ballpark of 0.0508, we'll call it. Again, these are moles per liter, really, of nitrogen, technically the molarity of our nitrogen gas. Any questions so far? Now, this is where, at this point, if we think about what we're looking for, which is grams per liter, we're good to go on the bottom. Top, we just need to get the grams. What do we have on top is moles. So again, you can think about it like a conversion. I need to go from moles to grams. Again, that is our molar mass, right? That allows us to do that conversion like we've seen many times. So we would want to get the molar mass of N2 in this case. Remember, nitrogen is diatomic. That gets us 2 times 1401. 2802 in terms of our molar mass, again, grams per mole. And really, it's just a conversion sort of problem at this point. We want the moles to cancel. So 28.02 grams per mole. Moles will cancel. And that will leave us 0.050508. 1.42. Again, the units we're left with is what we are looking for, which is grams per liter. So Again, if you can't remember that formula or not sure, you could use really the ideal gas law and really kind of just turn it into like a conversion problem where you're changing units and getting things to the right units. Any questions on any of those steps? Obviously, if you plug that into the same equation that we just saw on the other slide, because they're really based off of the same thing, you should get the same answer. Any questions on any of those steps? Okay. Let's roll back the other way here. And why don't you try this one here? This one, we're looking for the molar mass. So see what you come up with. Again, a reminder that the molar mass is units of grams per mole is what you're looking for in this particular problem. So see what you come up with. I don't think you need any other information, I believe. I think you should have everything you need. Again, approaching it, I'm going to approach it sort of really as a conversion factor type problem. Again, if you can't remember that specific formula that we saw last time, this is the way you kind of should approach the problem. First off, let's approach the problem by looking at what we're trying to find, which is grams per mole. And let's read through the problem and see what's given to us. We have a volume that's 2.1 liters. We have grams, that is 4.65. And we have a pressure that is 1 atmosphere and a temperature that's 27 degrees Celsius. So we're looking for the molar mass. So right off the bat, straight from the problem, we actually have the grams. We don't even need to convert it to moles or anything in this particular case. We actually want it in grams. So we do have the top part of it. And if you're able to sort of recognize that, you'll then know that really you need to figure out the moles. So where can I sort of figure out moles with a gas problem? I only got one pressure, one volume, one temperature. I should look at the ideal gas law. Seems like a good idea. I have a volume given to me, I have a pressure given to me, I have a temperature given to me, and I always have R, which, as you can then see, leaves us the missing piece that we really need here. So again, you kind of want to approach these guys if you can't remember those things or really don't want to remember those formulas. You could kind of approach really density and molar mass as more of a conversion problem sort of approach here. Pretty much at this point, we would want to solve for N. We're going to bring RT to the other side, giving us PV over RT. We just got to make sure unit-wise we're okay. Atmospheres is all good. Liters is all good. Like typical, right? Our temperature is not so good there. That's going to give us 300 Kelvin again. Now we're good. We could put in. So our pressure being 1 atmosphere, our volume being 2.1 liters, divided by our gas constant that we always have, and our temperature here, which is 300 Kelvin. Doing some math here and looking at units, we got atmospheres that are gone, we got liters that are gone, and we got Kelvin that are gone. Again, leaving us moles, which is really good because that obviously is what we're looking for. So taking 1 times 2.1 divided by 0.08206 divided by 300, going to get us moles of 0.0853, we'll call it, moles of our gas. Any questions up to that point? We obviously now have really kind of both components that we need to figure out our molar mass. So the molar mass here would be our grams per mole, putting in our grams that was given to us and usually given to you in these type of questions, 4.65, 0.0853 moles, going to end up with 4.65 divided by 0.0853. We'll call it 54.5. Remember that the units here do not cancel, which is good because those are the units you're looking for, which are molar mass and grams per mole. Any question on any part of solving that problem there? Are calculating density or molar mass for a gas?
I've just got a quick question. I ran this problem from the other direction with the molar mass equals dRT over P, and I came out to my number of moles as 0.0855. I'm off by just a little bit. Do you know where I went wrong?
I don't think he probably went wrong. It's probably my best educated guess would be it's just probably just the rounding somewhere.
Okay,
You might have
thanks,
rounded.
Greg.
I probably didn't. Usually on my calculator, I don't round too much, so I can maybe continue with the number. So my guess, if you're that close in terms of your moles, is probably just a slight difference of where you rounded, or maybe if you use, I don't know if you use 0.0821 for R versus the 206, that also
I,
could
I
cause
did. I did use 0.0821.
so that could cause a little bit of the difference as well. So
Okay,
not a big
thank you.
Yep. Other questions? Okay. So obviously you need to be able to do those two things, and then like I said, sometimes it's maybe just easier not to memorize the formula if you don't want to, and just kind of use it and solve it this way. But either way, again, should really get you pretty close to the same answer, or should get you really the same answer. All right, then the next thing we're going to talk about is actually stoichiometry involving gases. The good news, bad news on stoichiometry is it's stoichiometry now, but the good news is it's pretty much solved the same way as a regular stoichiometry problem. You could potentially have a limiting reagent problem as well, but probably most of the time these will follow really the same approach as a regular stoichiometry problem. So if you remember sort of our 4 steps for a sort of basic stoichiometry problem is obviously we want to have a balanced equation. We obviously want to convert to moles, whatever they give us. We want to do our mole to mole relationship, really going to the balanced equation using those coefficients. And then we want to convert from moles to some other unit. So where does sort of the gas part of it come in? How is it different? It's different because somewhere along in these steps, a lot of times at the end, you could at the beginning as well, but a lot of times at the end, you will basically use like the ideal gas law. And usually if you're using the ideal gas law at the end, you will be solving for volume a lot of times. That's a very common sort of question, how much volume of a gas is produced. You could potentially use the ideal gas law up front as a way of solving for moles, right? Again, a different way of sort of getting moles rather than grams to moles and stuff like that. So those are the two sort of common places where you would sort of use the ideal gas law. I would say probably most of the time it's like at the end, but you could potentially, again, kind of use it at the beginning as well. So we would want to approach these sort of the exact same way as we would approach, a regular stoichiometry problem. So for example, here, if we look at this equation, what is the volume of CO2 that's produced at 37 degrees Celsius and 1 atmosphere when 5.6 grams of glucose reacts with, excuse me, reacts with the O2 there and it gets used up in this reaction. So we have a couple of things going. We do want to get to, obviously, in this case, the CO2, which is a gas. So as soon as I see gas and I'm looking for a volume, that makes me really think I'm going to be using this here at the end. And that means that basically I have V is equal to nRT over P. So let's think about what information is given to us in this particular problem. We see that we definitely have a temperature that's 37 degrees Celsius. So that's a check. We have 1 atmosphere, which is a pressure. So that's like all of our sort of gas information. So that's a pressure. We always have R, and we're looking for volume. So what we're really missing in terms of the CO2 is the moles of CO2, right? And that's really where the stoichiometry part comes from. The last piece of information that we have is basically how many grams of glucose, which is this guy over here, by the way. So this is where our stoichiometry is going to come into play. We're going to be able to hopefully go from really grams of glucose to moles of CO2. That will then allow us to use the ideal gas law and really all of our sort of gas information over here to really solve this problem and find out really how much volume of CO2 is produced. So let's talk about sort of these steps. Really, first step along the way is the same thing. We want to start with a balanced equation. I see some coefficients there, so I'm feeling very good about it that it's balanced. Obviously, like normal, if you don't see coefficients, you probably should make sure that it is balanced. Second step is to convert to moles. And in this particular case, it is like a regular stoichiometry problem. We have 5.6 grams of glucose. So in order to do that right, we need to go to the periodic table and find the molar mass of glucose. That is 6 carbons at 12.01 each, plus 12 hydrogens at 1.008 each, and 6 oxygens at 16. That gives us a grand total of 180.2. Remember, we want the grams to go away, so 180.2 grams on the bottom, moles up on top here. So again, from the periodic table, the molar mass. You could get an answer at this point, so we'll just kind of do it step by step so you can see the steps again. Dividing it out gets us ballpark figure here, 0.0311 moles of our glucose. Again, probably not going to round on my calculator. But we also need to remember that this is moles of glucose, and that is not what we need, right? We need moles of CO2 in this case. So this is really where the stoichiometry part comes into play. And that is the third part, right? Which is the mole to mole relationship. So looking at this equation here, we could get that mole to mole relationship from the coefficients. And we see that 1 mole of C6H12O6 gets us 6 moles of CO2. So in this case, we would continue on. And again, I'm continuing on with the non-rounded number in my calculator, 6H12O6. We want to get rid of the glucose, so we do want to put moles of glucose on the bottom. And we want moles of our CO2 up on top. Moles of glucose are going to cancel. Basically, going to times that guy by 6. And that'll get us something like 0.186 moles of CO2. Any questions so far? So last step is to take that now and convert that into the units we're looking for. Now we do have the moles of CO2. And again, this is really in this particular problem where it varies from a run-of-the-mill stoichiometry problem. We're going to again use our ideal gas law here. We're going to solve for volume. And now we're going to use our gas information, including the moles that we just calculated. We're going to use our R. We're going to use our temperature, which I neglected to convert to Kelvin. So that looks like a 310. So here we go, 310 Kelvin. Adding the 273 to that, 310 Kelvin. All divided by our pressure, which was also given to us in the problem, which is 1 atmosphere. Again, looking at units, atmospheres cancel. We got some moles to cancel. We got some Kelvin to cancel, leaving us liters, which is really good because obviously we're looking for a volume, and that gets us, looks like 4.73 as our liters of CO2 that would be produced in this case. Any questions on any of those steps there? Hopefully you could recognize some of these steps from our stoichiometry conversation we had, but it really is, again, balanced equation, check. Convert to moles, check. Mole to mole relationship from the equation, just like a normal stoichiometry problem. And lastly, convert to some other unit. This is, again, probably 9 times out of 10 where you will incorporate the ideal gas law is at that last step, that kind of 4th step. So instead of, again, using moles and molar mass to get grams, because it's a gas, a more useful unit is volume. So again, here we incorporate using the ideal gas law to figure that out. Any questions on any of those steps there? And it pretty much means the same thing here. Obviously, glucose, if you threw in there 5.6 grams of glucose, you would expect obviously that many liters of CO2 to be produced. It technically would also be your theoretical yield of CO2 in this reaction, right? Also, this is a basic stoichiometry problem, which tells us in this particular reaction, glucose is the limiting reagent and O2 would be the excess reagent. And that's why we didn't have to do any type of figuring out limiting reagents, because just like those regular stoichiometry problems, we really were only given one piece of information, right, that allowed us to get to moles. And that's how we know it's a kind of basic stoichiometry problem versus one where, again, both reagents you could get to moles. So why don't you try one here, see what you come up with. We got a little reaction of magnesium with hydrochloric acid. Also experiment 12, I think is that experiment. We put some magnesium, hydrochloric acid, going to produce some hydrogen gas. We want to know how much hydrogen gas would we produce there at STP conditions, and a couple of numbers that might be helpful for you in terms of periodic table. Magnesium is 2431, it looks like. And maybe hydrogen 1.008. I think that's probably all you need, I think. I'll do chlorine, but I don't really think you need it. 3545 grams per mole. All right, take a couple minutes, see what you come up with here. And let's take a look and see how we're doing it. So really, again, a stoichiometry problem. We ultimately want to get to volume here of our hydrogen gas. Again, volume and gas is sort of an endpoint here for a calculation involving stoichiometry. Should sort of highlight that ideal gas law. And again, probably at the end here, we will be doing this similar type of calculation, kind of solving for volume. So we want to again kind of look at what else is given to us. So we do have STP given to us. Remember that is a 273 value, even though it just says STP for the temperature. And obviously our pressure is 1 atmosphere. So much like last time, we have a pressure given to us. We really have a temperature. We always have R. So just like last time, we're really missing the ability here to solve for the volume right up front, because we don't have the moles of hydrogen gas in this case, right? So we need the moles of hydrogen gas. So if we kind of take that out of the play, we pretty much just have 5 grams of magnesium left, which obviously we can't directly get to H2, but we can do some stoichiometry to get us there. So we'll start with our normal starting point, which is balancing equation. Again, I see a coefficient, so I'm hopeful that it is balanced. We're going to convert to moles, which is our next step. And in this case, this is really the only piece of information that we can actually convert to moles, right? We have enough information to do that. Also, because we have enough information to do that for magnesium, and it uses the keyword of excess HCl, that automatically tells us, again, the magnesium's our limiting reagent. This is our excess reagent. And we don't have to worry about figuring out limiting reagent, because in the problem, it pretty much just told you that. So we'll do it like normal here. We'll take our 5 grams of magnesium. We'll do a little dividing from the periodic table there, 2431 grams per mole of magnesium. Grams will cancel. That will yield us here 5 divided by 2431. Looks like a 0.206. So we do a little bit of rounding here. Remember, although we now into moles, but we're still moles of magnesium, which is not what we need, right? So we do need to get us to hydrogen. And again, that is where our stoichiometry part is going to come into play. From the equation, we got magnesium, we got hydrogen, and from that relationship from the equation, we could see that for every 1 mole of magnesium, we get 1 mole of H2. So that's not too bad. 0.206 moles of magnesium. Again, doing the stoichiometry part right here, 1 mole of magnesium, 1 mole of H2. I think I can do that. That is 0.206 moles of H2. Now that is now exactly what we need here to finish out what we're looking for. So really we're on part 4, which is convert these moles into the units you want. And again, in a traditional stoichiometry problem, we would use the molar mass to figure out grams. But here, since we're dealing with a gas, we're again going to really use our ideal gas law. We're going to solve for volume. We now have all the info that we need on that. We have our moles that we just calculated. We got our R. We got our temperature from the STP, which is 273. And we got our pressure from the STP, which is 1 atmosphere. Doing a little bit of calculation here. Looking like we're yielding like a 4.61 liters at this point, and that would be liters of H2 that would be produced. Again, like last time, that would actually be the theoretical yield of H2 in this particular case. Any questions on that calculation there? Now, I did it this sort of ideal gas law way. There is one last thing that you could have done if you wanted to, or maybe you did it. And that is because, kind of make a barrier here, we are at STP, which means because we're at STP here, we can basically leapfrog the ideal gas law. And we basically could use that relationship that 1 mole of a gas is 22.414 liters at STP, which means we really could just pick it up from right here and go 0.206 moles of H2 using our conversion there, 22.414 liters per mole. Moles cancel, 0.206 times 22.414, 4 point, in this case, again, slightly different because of some rounding, but 4.62 liters, essentially the same answer as what we got using the ideal gas law. Any questions on either of those ways or stoichiometry involving gases?